For this next problem, I want you to notice right off that there are 5 terms. And so because there are 5 terms, we don't have a factoring method that will work for that. Remember that grouping is the highest that we go with 4 terms. So we have to use our rational roots theorem on this one. And so let's go ahead and get started. My constant is 12 and my leading coefficient is that 3. So I want to say that P is 12 and Q is 3. And one thing that I want to go ahead and note here is that once we list all the possible zeros, we're going to delete some of them and just cross them out and say that we don't need to consider them because they're going to be duplicates of some of the ones that we wrote previously. The reason for that is because my Q value isn't equal to 1 anymore. So Q being a 3, my factors are 1 and 3. And for P, I have 1 and 12, 2 and 6, 3 and 4. Remember that these can be positives or negatives. So I would like for you to pause the video here and go ahead and write all of your factors of P, those 6, divided by 1. Don't forget your plus and minuses. We'll come back and do the other ones together. Okay, we had 6 p-values, so we should expect to have 6 possible zeros listed, but then with positives and negatives, it's actually 12. Let's go ahead and do the second part of this, which is now we have to consider that Q could be 3. So all of the same p-values, 1, but over 3, 2 over 3, still using positives and negatives, 3 over 3, 4 over 3, plus and minus 6 over 3, and plus or minus 12 over 3. We can eliminate some of the possibilities because they actually are stated twice. And so let's look at our fractions that are over 3, that bottom row. And I notice that I have a 3 divided by 3. Well, if I simplify that, it's the same as 1 over 1. And so that's what we consider a duplicate. And so we can just cross that out and we don't need to think about it anymore. Another one that has that is 6 over 3 because that would be 2. And 12 over 3 is 4. And both of those are already accounted for in our first row. So we can eliminate those and at least eliminate 3 fractions, so 6 possible zeros. But now what we're going to do is we are going to look at our graph in Desmos to see what the reasonable solutions are going to be. So let's take a look. We've got some fractions going on here. All right. So when we have things that are kind of ugly fractions like that, that is not something that we want to stick into our synthetic division. Fortunately, though, I do see one integer. I see a 1. So even though we know that we have 3 other places where we have solution, the best that we can note is kind of what numbers those are in between. So for example, this first one is in between -4 and -3, between 0 and -1, and between 3 and 4. So we can note that, but I'm going to want to use the 1 to do my synthetic division. Okay, so back over here, we can say that we are between -3 and -4. We were also between -1 and 0. The other one that was between +3 and +4, and then we had that nice integer 1. I'm going to use that one for my synthetic division. So we will go ahead and test using synthetic division and see what our numbers are. Let's go ahead and do our synthetic division. I want to check and see if I have all of my terms or if I need to add any of those placeholder zeros. So we're starting with 4, 3, 2, 1, and 0. I have every single one of those, so I don't need any placeholder zeros this time. 3, -2, -37, +24, and 12. I'm going to do the same thing I've been doing, bring down the 3, multiply to get 3, add to 1, multiply to 1, which adds to negative 36. That multiplies to negative 36, leaving me with a negative 12, multiplies to negative 12 and gets 0. Again, we are just confirming this. We really already knew it because we saw it on the graph. However, we can't report decimal answers for all of our other possible zeros or actual zeros, and so we have to use this method and factor and see what's going on with those things that had the decimals. So we'll get constant x, x squared, and x to the third. Remember that we used the solution of x equals 1. That gives us a factor of x minus 1 equals 0 when we move the 1 to the other side by subtracting. So this is our factor that we will use below in our partially factored form. So we'll say x minus 1, and then we want to go ahead and recombine our variables and our coefficients. So I have 3x cubed plus x squared minus 36x and minus 12, and that's going to equal 0. We can also make a note that we got this by using the division step above. Now I want to keep solving or keep factoring so that I can solve. And I notice that I have 4 terms left. 1, 2, 3, 4. That leads me to the grouping method of solving, and so we use a factor box. I'll write each of my factors in one of the spots in the box. 3x cubed, x squared, minus 36x, and minus 12. And then I'm ready to find my GCFs. I will have an x squared and a negative 12. I have a 3x and a 1 as my GCFs across each row and down each column. So now I have factored further. I still have the x minus 1, don't forget about that one. And then we have 3x plus 1 and x squared minus 12, and the whole thing equals 0. Now I have 2 linear terms here. They have a 1 as an exponent, but x squared minus 12, well, that has got a squared on it, so we need to investigate further. We have 2 terms and subtraction. That leads us to using either difference of 2 squares or difference of 2 cubes, but we have to have 2 perfect cubes or 2 perfect squares to do that. X squared is a perfect square, but 12 isn't a perfect anything. So we can't factor this any further. We're going to be ready to solve, but solving is going to look a little bit different for that particular factor. We can go ahead and set each of these equal to 0. So I'll say x minus 1 equals 0, 3x plus 1 equals 0, and x squared minus 12 equals 0. This first one, similar to what we've done on all the previous ones, I add 1 to both sides and get x is equal to 1. The second one, need to do a couple of steps because I first need to subtract 1 from both sides. That will give me 3x equals negative 1, and then I need to divide by 3 to give me what x is, and x is going to be negative 1/3, so a fraction. That was, remember, one of those decimals that we got whenever we looked at Desmos. Negative 0.0333, and that is negative 1/3. Now, this one is going to give us our other 2 decimal answers, but we can't write decimals. We need to have the precise exact form. No rounding. So here's what we're going to do. We're going to move the 12 to the other side, just like we've done on the other problems. Move the constant over. But now I have an x squared instead of an x. And so I have x squared equals 12, but I have the skills for this. I know that back in our quadratics chapter, we learned that we could solve by square roots if we had a perfect square on one side and something else or everything else on the other side. So I can cancel out a square root and a squared because those are opposites of each other. That leaves me with x. That's what I want. But don't forget that when we do that, our stuff on the other side has to have a positive or negative added to it, because we don't know if it was two positive things that multiplied together to be x or two negative things that multiplied together to be x squared. So we've got to take into account both possibilities. All right, this is a solution, but it's not in its most simplified form. Remember that even if we don't have a perfect square, we need to look for hidden perfect squares within it using a factor tree. 4 and 3, 3 is prime. 4 breaks into 2 and 2, and both of those are prime. So now I can say that I have a set of 2 2s, and then I have a 3. I can take these 2 2s and actually do the operation of taking the square root. So 2 times 2 is 4, and I know that the square root of 4 is 2. So it comes to the outside, but the 3 has to stay. So I can rewrite square root of 12 as 2 square root of 3. So x is equal to positive or negative 2 square root of 3. And that's my other two answers. Those were the other two decimals that I saw on my graph. Remember, this is actually two solutions, one with a positive 2 square root of 3 and the other is a negative 2 square root of 3. I saw 4 solutions on my graph, and I actually knew 4 solutions from the beginning because I had a 4th degree polynomial.